Great. So basically, we just have a couple more concepts to talk about over the course of the next 5 class periods. My plan is to give you next Friday off as a time to work on your take-home, because I'll give you your take-home later this week. Give it the time, and then time to come ask me questions if you've got questions on it. Once you have some time to look at it ahead of time, work on it, and if you've got questions, you can come just to my office and ask questions at least during that particular time. So like I said, my plan is to give that to you probably Wednesday, and then we'll finish up with what we're going to cover as far as stuff by next Wednesday.
So next Friday we don't have class.
Next Friday you don't have class. And that'll be time to work on your take-home. And then your take-home will be due, what is our finals scheduled for Wednesday of finals week? So it'll be due that day. So anyway, as far as that goes, that's about all I got for that.
When will numericals be due?
Say it again.
When will numericals?
Probably that Tuesday, because I'm pretty sure that's when it's scheduled, yeah.
Okay.
I got a good thing to work on for that too. I'm kind of excited about it. So at least I think it's interesting. That probably means that you all will think it sucks, but I think it's kind of fun. Guess we'll find out. It won't be cubic splines, I can tell you that. You got them all down now? Well, you can do cubic splines if you want, I suppose. All right. So we need to talk more about this efficiency idea, get into some other certain types of another quality of statistics, and then talk about how we can get a handle on power of tests, of hypothesis tests. So for today, we want to talk a little bit about minimum variance unbiased estimators. Or we'll abbreviate MVUE. So we've talked about relative efficiency. You had a problem on the exam of computing relative efficiency between 2 different estimators for a population mean based on a sample. And you were asked which one was more efficient based on the size of the variance. But in general, how do you know if you have a estimator for whatever parameter you're trying to estimate, how do you know that it's the best that you can get as far as the variance goes? How do you know it's the most efficient? Well, again, we define efficiency in terms of variance. So to be able to know that something is the most efficient, you want its variance to be as small as possible. Okay? So to that end, what we're going to be gunning for today is to figure out a bound on the variance for any estimator that you come across. Okay? So to that end, let's start with, so we've got some background that we have to do. So we're going to let y be a random variable. That random variable is going to be the partial with respect to theta of the natural log of the PDF of x that happens to have theta in it. I know this looks bizarre, but it's going to turn out that this particular computation is involved in finding the lower bound on the variance of any estimator. Okay, so as far as the motivation goes, there's not a lot of motivation right this second, but we're going to get to the point where, just trust me on the fact that we're going to get to the point where we need this idea to get a lower bound on all the possible variances that you can have. Okay? So bear with me as we go through this stuff. So if we want to compute the expected value of y, the expected value of y looks like, of course, whether it's discrete or it's continuous, you would compute the expected value in the same way. I'm going to write it like it's continuous, so I'll use an integral sign, but know that you could also write it if it were discrete and using a sum sign. It still would be the same idea. So we would take the integral over your sample space of, well, it'd be y times its PDF. Well, y is defined in terms of x. It's a function of x, right? So this would be the partial with respect to theta. What are you doing? Stop. Of the function, and then times the PDF. That's how we do expected value, right? You take the function times the PDF and either integrate it or sum it over the space. Yeah? All right, so this doesn't look like anything that I can compute without knowing some specific functions, so I have to be a little bit clever. All right, so remember that, of course, if we take the integral over the entire sample space of a PDF, what do we have to get? No matter what the PDF is, we have to get 1, right? So if I take the partial with respect to theta on both sides, what's the right-hand side going to become? 0. Good. We agree? All right. Now what I would like to do is move this derivative with respect to theta inside the integral. The reason why I would like to move that derivative with respect to theta inside the integral is because up here, when I'm doing an expected value of y, I have the derivative with respect to theta inside the integral, right? In order to be able to do that, in order to be able to switch the order of the differentiation and the integration, I need to make sure that my sample space doesn't involve theta. Okay. Now remember that that's not always a given, right? When we've done that specific example of being uniform on 0 to theta, when we've done examples where we have uniform on 0 to theta, notice theta is involved in my sample space, right? As theta changes, the sample space changes. Okay. In that particular scenario, I wouldn't be able to do this reversing of the order. Okay. So we actually refer to this type of a variable as regular. Okay. So we're going to assume that x is regular, which means that the sample space does not depend on theta. This allows us to switch the order of the integration and the differentiation. And again, the whole reason why I want to make sure I can do that is so that I can get that derivative on the inside, because that's what the formula looks like for the expected value of y. So assuming it's regular, we can move this on the inside. Oops. Yeah, that's right. I can flip the order and move it there and put it on the function and then integrate, versus having to integrate and then differentiate. You've seen this before with doing double integrals or triple integrals. We've had double integrals where we could split it into piece with just an x and piece with just a y and multiply it together. But to be able to do that, we had to have the constants just be constants on the the limits of integration and not a function of one of the other variables? This is the same kind of concept, right? Notice here, this says I'm going to differentiate my theta first and then integrate. Well, if this involved theta, I could have some issues because I didn't differentiate it on the outside. There's some chain rule with respect to differentiation ideas that you'd have to worry about, which we're not going to worry about because we're assuming we don't have that kind of variable. All right, anyway, well, how does this now compare to this? What happens when you take the derivative of the natural log? What do you get? Just in general, what do you get when you differentiate natural log? You know, 1 over the inside times the derivative of the inside, right? Well, if I take 1 over the inside, notice those will cancel, won't they? And all you're left with is the derivative of the inside, which is exactly this, right? So this is equal, and we already know that this is still equal to 0. So this piece right here is the derivative of the natural log of f of x in theta, times the PDF. Those two things are equal expressions. So that tells us that our expected value of y is 0.
We did some of this the other day.
Did I do this the other day?
And you had d theta that last time instead of dx.
It should be dx. Yeah, d theta is wrong. I didn't realize I had done this the other day. Sorry about that. Well, it doesn't hurt that I've done it again, does it? All right. So we had to do the expected value. I didn't do the variance yet, though, did I? For this
No,
one?
we had only gotten to what you just did.
What is what I just did? Okay. Of course, one of the reasons why we need the expected value is because the expected value is part of the variance formula, right? We agree? Now, since the expected value is 0, all we really need to do is just compute the expected value of y squared and we'll be done, right? That's all we need, right? Because we'll subtract off 0 squared. Okay? So to get at that, we know that the expected value is just going to be, certainly, the expected value of y squared, this will be the variance now of y, will be the integral over the sample space of the partial of the natural log of this thing squared times f of that dx right? Because all we're doing is doing y squared, right? Now again, this might not be the easiest way to compute. I mean, we could do it in this case, right? If we know the PDF, we could take the natural log, we could take its partial, we could square it, and we can multiply by the PDF and be done, right? We could certainly do that, right? But that may not necessarily be the easiest way to do it. So what we're going to do at this point is see if there's another formulation for the variance that we could use. All right, so going back up to this line right here, I still know that that line is 0, right? If we take the partial with respect to theta again of this, I still have to get 0 on the right-hand side. Because when I differentiate 0, we get 0. All right, so now we're going to move this partial inside the integral. Again, we can do that because we're assuming we have a regular random variable. And in particular, all by regular we mean is, again, that the sample space doesn't depend on the theta. Okay. When I move this in, though, I want to take that means I have to take the derivative of the entire integrand, right? Notice the integrand is a product. So to be able to do the derivative, I have to do a product rule, right? We agree? So when we do the product rule here, we will have, it'll be the second derivative with respect to theta times the PDF. And then it'll be plus the first derivative of the natural log times the partial of the PDF. And that whole thing is still equal to 0. So again, this is derivative of the first. If they just think about the product rule, that's f prime, that's g, that's f, that's g prime, right? Everybody see that? We agree with that? It's messy, but that's what we get, yes? All right, so let's look at this piece again, this guy right here. Well, we just had that not too long ago. What did we say that looked like? That was this piece, wasn't it? Wasn't it? Right? This is this piece here. Right? So this was equal to that. So notice here, if I rewrite the second part, this will be the second partial, sorry, of the natural log function times the PDF plus the first partial of the natural log function squared times the PDF. And that's still equal to 0. And again, the reason for that is, I'll write it above this little brace. That's because that is equal to the partial of the log times the PDF. It's a logarithmic differentiation property. All right, for this part of the integrand now, what did we say that that was equal to? Looking at the top of the screen, what did we say that was equal to? That's the variance, right? So notice that this piece here, if I move it to the other side, also has to be the variance, doesn't it? So instead of doing a squared, I can do essentially the second partial, take the negative of it, and I get the same information. Okay? So we also see from this that the variance of y is equal to the expected value, or well, it's definitely equal to the expected value of the partial of the natural log function squared, but it's also equal to the negative of the expected value of the second partial of the log function. They both give you the same information. So we have a name for this. Of course we do. we have a name for this. We refer to this as the Fisher information. The notation for that is capital I of theta, and that's the variance of this y variable. Phew, okay. About halfway home. I know. It's exhausting. I agree. All right. I told you, that's why I was saving this for the take-home part, right? I didn't. There's a lot of stuff, right? Okay. So, what do we use this for? Again, we're trying to get to the point of trying to get a lower bound on an estimator, right? Now, the estimators are always computed off of some random sample, correct? Like when we did the maximum likelihood estimator for an exponential distribution, the parameter we were trying to estimate was the theta. We use the mean of the sample because the mean of an exponential distribution is theta, right? We've done estimators, correct? All right, so this is based on just one particular random variable, the x, okay? So let's let x1, x2 out to xn be a random sample from a regular random variable x and we're going to let v be the partial with respect to theta of the natural log of the joint density function of the xn's. All right, well, let's just look at this. How do we get the joint density function from a random sample? If they're random, what do you know about, if we think about each of them as an individual random variable, what do you know about those random variables if it's a random sample? They have to be what? Independent. They're independent, right? And they all have the same distribution, don't they? Because they've got the random sample taken from the same random variable, right? So they're independent and they're identically distributed. So how do we come up with the joint density function then? What do we need to do? If they're independent, what do you do with the individual density functions? Multiply them together, right? And they're all identical. So this will be, v will be the partial with respect to theta of the natural log of a product of the individual joint density, or the individual probability density functions. Right? But now we have the log of a product. How do you take the log of a product? Sum, good. So this will equal the partial with respect to theta of the sum of the logs. I should have put an I on there, but it doesn't really matter because all of them are identically distributed. Oops. So far, so good? Just change the log of a product to the sum of the logs? Yeah? What can I do with this? Put it inside because it behaves nicely with respect to sums, right? I can take this and move it inside. I said I could move it inside and then didn't. Which random variable is this now? What did we just define that as earlier? Well, it's close. I mean, that's where we're headed. But what variable was that I called this? I gave it a letter name earlier.
Oh,
Not V. There was the Y, wasn't it? This is the Y variable, isn't it? So this is just the sum of a bunch of Y's, right? Which is just n times Y. And really, I've got a bunch of independent Y's. I don't really want to think of it this way. I want to think of them as independent. So, but that's really what this is, right? It's just Y added to itself a bunch of times. But really, I'm thinking of a Y1 associated with X1, a Y2 associated with X2, and so on down the line. Okay, so I don't want to think about it as n copies of Y, because we're going to take the variance here in a second. I want to think about it as a sum of independent Y's. Does that make sense? Okay. So I don't want to think about it quite this way, but that's really what that is, isn't it? Okay. All right. So thinking about it that way, though, what's the expected value of V? What was the expected value for each of the Y's? What did we compute the expected value of the Y's? 0, right? So the expected value of your V is 0. What about the variance of V? Well, each Y has variance, that's that Fisher information, right? So there's n of them, and they're all independent, so this will just be n times your Fisher information. This is why I didn't want to think about it as just n times Y, because usually when you think about it as n times Y, when you pull the n out, it squares it, right? And that's not what we're really doing. They're independent Y's, and we're adding them up, so we just have to add the variances. Not using the same Y and multiplying it by n, not scaling it, right? We're taking independent ones and adding them together. All right. Okay, so we're at this point. So let's look at an actual estimator now. So let's suppose that theta hat is some function of your random sample. I need to be unbiased. All right, so since it's unbiased, we know that the expected value of the theta hat has to be the theta, right? And then if we're computing expected value, of course, we have to do a multiple integral because I have to do the expected value of this function, don't I? Right? Do you agree with that? If I want to do expected value, I've got to do the expected value of this function. That function's over some joint PDF, right? So this will be a bunch of integrals all over the same sample space, though, right? Or a bunch of sums. I would go over the sample space for each of your x's, but all your x's have the same distribution because it's a random sample from x, right? So I do the integral over the sample space for all of those things of the function times the PDF. And then, of course, this will be dx1 out to dxn. All right, so now I want to differentiate both sides with respect to theta. What do you get on the left-hand side when you differentiate with respect to theta? You get 1, right? You agree? So I get 1. Now again, we're using a regular random variable, meaning that the theta the s's don't depend on the theta. So I can take the partial and move it to the inside. That's step 1, right? Right? Now, does your u function involve theta? No, it's a sample on the statistic, or it's a statistic based on the sample. I said that backwards. Okay, it's a statistic based on the sample, the x1, the xn. There's no theta. So as far as a theta is concerned, that's a constant. So all I need to do is differentiate the PDF, right? But we know that the PDF, the derivative with respect to theta of the PDF is the same as the derivative of that log function times the PDF, right? So I can rewrite this as u of x1 out to xn times the partial of the log function times the PDF dx1 out to dxn. Oh, sorry. This is not just a single PDF. This is the joint PDF. Sorry. I'm not going to rewrite the whole thing. That's the joint PDF. Since I'm doing the expected value over the whole thing, that has to be the joint PDF. So this is also the joint PDF. Oops. It has to be the joint PDF because I want this to be the V, right?
So in the above one, you're supposed to have that natural log instead.
No, it's the notation's right. It should just be f of x1, x2, x3 out to xn. It should be the joint PDF there, not just f of x.
Okay.
That should be joint PDF. And I don't want to have to rewrite the whole thing. That's why I just wrote joint above it. Okay. All right, so notice that we've got function times PDF. So this is an expected value, right? This is theta hat. This is V. Right? That was our V function. That was how we defined our V. Because it was the log of the joint PDF. Right? The derivative of the joint PDF. So this whole thing is expected value of theta hat times V. Now this is the product of two random variables, if you think about it that way. What formula do we have from stuff that we learned last semester and talked about earlier this semester? What formula do we have involves the expected value of x times y? And then subtracted something else off of it. It's covariance, right? Covariance is expected value of xy minus expected value of x times expected value of y, right? Well, in this case, if we did expected value of theta hat times expected value of v, what would we get? What is the expected value of v? It's 0, right? So this expected value of theta hat times v is simply, oops, the covariance of theta hat and v. Right? And the reason for that is because the expected value of v is 0. So we don't have that difference on the end. Okay? We have another way to express covariance. Remember we had correlation? So covariance would be the correlation times the product of the standard deviations. That was a property we had last semester, I believe, but we talked about this, right? And also, what do we know about rho? What do we know about correlation? What's it always have to be in between? -1 and 1, right? So if I remove the rho here, this product is bigger than 1, correct? Right? Certainly this has to be this can't be negative because these are both positive. And if I remove this rho, this would have to be bigger than 1. So we get 1 is less than or equal to the product of the standard deviations. Of course, if we square both sides, it doesn't change anything, does it? It doesn't change the order of the inequality, and it won't change the value. So I might as well say that the product of the variances has to be bigger than or equal to 1. Right? Now, look at this. This is the variance of our estimator. This is the variance of that very specific random variable we created. Right? If we rearrange this, this says that the variance of our estimator must be at least as big as 1 over the variance of V, which is 1 over n times that Fisher information. Right? This now gives us a lower bound on our variance. Okay? If we write this out, I mean, I could write it out in terms of the expected value. This is what? A negative 1 over n times the expected value of the partial of the log of your PDF. Oops, write it this way. So notice that you now have a minimum that your variance can possibly take on. Period. This is as small as your variance can possibly get. Because this PDF is determined by what the random variable is, right? Right? We can certainly, sorry, this is second derivative. Second derivative, sorry, this should be second partial. The PDF is given to us, it's based on the distribution, right? Do we agree? It's based on the distribution. I can take the log of it, I can take the second partial of it, I can find its expected value. All of that is based on the actual PDF we're given. So this is a lower bound on the variance of any estimator. Okay? This is what's referred to as the Rao Cramer Inequality. So let's see if we can do a problem where we actually find this lower bound. This is on that extra sheet that I gave you the other day. This is 11-27. The book that I took it out of it calls it the Cramer-Rao lower bound. Yours calls it the Rao-Cramer inequality. I'm going to go with Rao-Cramer inequality. So our f of x is 3 theta squared x, 3 theta x squared e to the minus theta x cubed. And our sample space goes from 0 to infinity. All right, so if we're gonna calculate this lower bound, the first thing we have to do is take the log and take two derivatives with respect to theta. Okay, so if we take the log of our f of x, and I'm not going to write the with theta in it because it just gets redundant because we need to know we're doing this with respect to theta anyway. Notice we've got a product here, don't we? I got a 3, a theta, an x squared, and an e to the minus theta x cubed. So I'll have log of 3 plus log of theta plus 2 log of x minus theta x cubed. I just took the log of each piece, made it a sum, and then log and e cancel each other out, yes? I also brought the 2 down in front with the x, but it turns out it won't matter here in a second. You okay with that? All right. We need to take two partials with respect to theta. Well, the first one's going to eliminate a couple of terms right away, isn't it? Partial with respect to theta, that first term is 0. How about the second term? Okay, third term? Gone, good. Fourth term? Negative x cubed, good. Now I got to take a second derivative. What do we get? Apparently quiet's what we get. Cool, good. All right. Notice, by the way, that when you do the second partials, you're going to be getting negatives in them, which is why there's a negative up in that variance formula up here. You got to make it positive, right? If it's variance. So when you do these second partials, you're going to get negatives a lot of times, and the negative on top will make it positive. Always has to be a positive value. Okay. All right. So let's do our expected value now. Oops. So this will be the integral from 0 to infinity of negative 1 over theta squared times the PDF. This one's pretty easy. We're integrating with respect to x, so what is this as far as the integral is concerned? As far as the integral is concerned, what kind of an object is this? Constant, right? So we can pop that out in front. And then what are we integrating? What are we integrating? If we pop that out in front, what are we integrating? The PDF over the sample space, right? So after we pop that constant out in front, what does the integral become? 1. So this answer is just negative 1 over theta squared. Does that make sense?
Is that always going to be like that? Where part of it is going to be the function?
Part of, yeah, it's always, there's always going to be a piece of it's going to be the function. Sometimes you have to do a little bit more work with the integrals, but this one was pretty easy. Okay. So when we did our, so this, the denominator then, our variance for our theta hat will be greater than or equal to the negative 1 over the n times the negative 1 over theta squared. So we just get theta squared over n when we simplify. So the point of this is, there is a point. The point of this is, you're trying to look for, hopefully, the most efficient estimators that you can find. Right? Well, the most efficient estimators you can find for this particular example will be ones where the variance is theta squared over n. That's the idea. That will be the most efficient estimator that you can find. Okay? So, for example, in a lot of problems, when you find the maximum likelihood estimator, it turns out the maximum likelihood estimator has that variance as your lower bound. So your maximum likelihood estimator is also a minimum variance unbiased estimator, an MVUE. Okay. There's a lot of information, I know. Okay. So we'll do another example or two next time, as well as get into sufficient statistics. And then after that, we'll get into power. I was going to ask you, do you want another assignment for a grade, or would you rather give you some problems to work on and then provide solutions? The second one? Okay, I can do that. So that you have some examples to go off of for your take-home, is what I was thinking. So, all right. We'll do more of this next time. Can you see why I wanted to save that for after the last test?
So, next week we don't have numerical versus stats on Friday.
Correct.
We're going to get the numerical take home.